Let's talk about taking derivatives of functions. And specifically, I want to take derivatives of functions that are the product of two other functions. So let h of x equal f of x times g of x. Then what I'm trying to do is I'm trying to recognize, oh, if I come across a new function out in the wild, out there in the world somewhere, in your homework or on a test, in physics, in chemistry, wherever I happen to find it, so I come up with some new h and I'm like, but I recognize this shape. I've seen this shape before. This is just two things glued together like this. I just have the product of two functions. Often you won't see the dot. So you'll have the product of two functions. We need the product rule to tell us how to correctly take the derivative of h. Then h prime of x is f prime of x times g of x plus f at x times, times g prime at x. Let me omit the of x's in that string of symbols because I feel like that's a bit of x heavy. So I'm just going to write h prime is equal to f prime g plus f g prime. Maybe the symmetry would work better for you as f g prime plus g prime f, because that way the prime stays stationary. And I just cycle through which one has the prime attached to it, right? So when we take derivatives of products of functions, we don't just get the product of the derivatives, right? This is not the same thing as, this is like a big red flashing box around the thing that I'm going to write right here. This is not equal to f prime g prime. It's absolutely not equal to f prime g prime. You have to do this other thing where you vary one at a time, let one of them take derivative at a time, and keep the other thing fixed. Okay. This isn't a video on why this is true. This is a video on the application of this. So what I'd like to do next is to write up two functions. We're going to do them in sequence, not simultaneously. So we're going to write up two functions and be like, I know how to deal with that function because I have the product rule, and we're just playing Legos. And I just love Legos. I'm going to leave the product rule up there because that seems like a great idea. So let's let, now I'm going to use a Greek letter here, alpha of x be equal to minus 4 x to the 7 times e to the x. Approach with a new function, right? A new function appears. And I'm going, how do I take the derivative of this thing? I really want alpha prime because it measures the instantaneous rate of change, because it's the derivative, because it gives me the slope of the tangent line, because it tells me where my function is increasing or decreasing, because with it I can compute intervals of increasing and decreasing of this function. I can compute optima, all sorts of fun things. So I'm like, I have to take the derivative of this thing. So I'm approaching with this new function, and using the difference quotient on this thing is going to suck. So let's not do that. But we can recognize that this thing is the product of two other functions. I've got building blocks. I've got my minus 4x to the 7, and I've got my e to the x. And I know how to take derivatives of those two functions separately, which means that I know how to take the derivative of them if they're multiplied together through our friend, the product rule. I just really like saying the power rule today. So now we're going to label these things. So let's just call this one F. Let's call this one G. Or like first and second are another one. So we got first and second maybe. So the product rule is going to tell me how to compute alpha prime as a function of x. So I'm going to take the derivative of the first. That's going to be minus 7 times 4, 28x to the 6. Times the second, g of x, unmodified, e to the x, plus f, unmodified f, minus 4x to the 7, g prime at x. Well, e to the x is this super cool function. And the thing that is so super cool about it right now is that its derivative is the same thing as the thing you started with, e to the x. So it doesn't really look like I took a derivative there, but most assuredly I took a derivative. So I don't know how much simplification there is available to us at this particular point. I could be like, I've got a plus and a minus right here. I don't know. So they both have an e to the x. Let's pull it out front. And they both have an x to the 6 in them. So I think I'll go that far. I think I'll take a 4 out too. How about we go minus 4 x to the 6 e to the x times, okay, the stuff that's left over in this term is just a 7. And then the part that's left over here is an x. So you get to choose whether you think that's any simpler or not. I just wanted to make sure that we at least played a little bit of simplification games. Because sometimes things look really different from each other, but they're actually the same function. So derivative of the first times the second plus the first times the derivative of the second is a way of thinking about and verbalizing that. So just be like methodical, do derivatives. You probably maybe at first want to write down that thing to remind yourself until you can build it into your brain so that you can just mechanically do it. Okay, let's do another one. It's going to be closely related to this one. So I'm going to call it alpha again, because that way I get to keep some of my framework here. Okay, so I'm going to start with a product of two functions. And then our first task is going to be to recognize that we have a product of two functions, that the product rule is in force. So that I don't make the mistake of accidentally just taking the two derivatives and multiplying them without using that plus in the middle, right? Because that's an easy mistake to make. I have made it many times. Many times. So my function I'm going to do this time is going to be e to the x times x cubed plus 5x. A new function appears. We want to compute its derivative. And we're going to do that by recognizing that this thing is a product of two things that I know how to take the derivative of already. Sweet. I know how to take the derivative of e to the x, and I know how to take the derivative of x cubed plus 5x. So let's product rule that thing up. So I'm going to do the derivative of the first, e to the x, times the derivative of the second, 3x squared plus 5. Because the 3 is coming down front, the 3 is turning into a 2. And then linear functions, you just pick up the coefficient in front of them. I really like taking derivatives of linear functions. Plus, now, f at x, that's this first part here, e to the x times I did them in the wrong order. I've got them flip-flopped back and I've got them flip-flopped. So this whole term is here and this whole term is here. That's okay. Addition commutes. So this one we'll just have regular old, this part right here, x cubed plus 5x. And I think I'm going to go ahead and factor out the e to the x to simplify this thing. Although in principle we're done already. So I'm going to have e to the x times, and I'm going to rewrite it. So I'm going to pull the biggest term forward, the highest term. So I'm going to have an x cubed plus 3x squared plus 5x plus 5. Yeah, and I'm not going to get any more simplification out of that at all. Steadfast application of this rule, making sure that you're only taking the derivative of one at a time. Just take the derivative of one piece at a time, and then leave the other one alone, and then add them together, and you'll get the right answer. So thanks for watching. Product rule. Go product rule. I really like the power rule today. Thank you. Bye.